And edge-to-edge tiling of the plane with more than one type of regular polygon and with identical vertex figures is called a semiregular tiling. And you can see some examples on this screen. Here's a couple other examples. The above semiregular tessellations are both made up of hexagons and triangles, but their vertex configuration is different. If you go around the vertex on the one on the left, you can see that we touch a triangle, then a hexagon, then a triangle, then another hexagon. But the one on the right, we go through triangle, 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 hexagon. So we're going through triangles and hexagons, but in different shapes, different numbers. And that's why we've named these semiregular tilings. The one on the left is a 3636 semiregular tiling. The one on the right is a 33336 semiregular tiling. To name a tessellation, you simply work your way around one vertex, counting the number of sides of the polygons that form that vertex. The trick is to go around the vertex in order so that the smallest numbers possible appear first. And that's why we wouldn't call our 33336 semiregular tessellation a 33633. All right, so the tessellation here is formed by two or more regular polygons. And the question is to name these polygons that surround each vertex. So if you go around a vertex, any vertex will be fine. I have a square here, and then there is an octagon and an octagon. So this is a 488 semiregular tessellation. Determine the number of angles that come together at each. So we have one square and two octagons. And we want to find the measures of these. Well, a square has a 90-degree angle. 90-degree angle. Let's try that again. The square has a 90-degree angle. As for octagons, so regular octagon, interior angles. If you recall, that's 180 times n minus 2, so times 8 minus 2, divided by the number of sides. So 180 times 6 over 8, and that comes out to be 135 degrees. So this angle right here is 135, and this angle here is 135. And if you notice, 90 plus 135 plus 135, it comes out to be 360. So that's going completely, that's one loop around a circle. That basically guarantees that we're going to completely cover our shape. So I guess we've already named this with the previous slide, but this is a 488 semiregular tessellation. All right, name each of these. So again, you just pick a vertex. So I'll pick, let's say that one. And you go around. You notice that you have 3 sides, 3 sides, 3 sides, 4 sides, 4 sides. So try and get the small, you're going around in order, but you try to get the smallest numbering possible. So this looks like a 3, 3, 3, 4, 4. The one on the right is also made up of squares and triangles. And I better use a different color. If I go around, I have, see here, there's 3 sides, 3 sides, 4 sides, 3 sides, 4 sides. So I know I'd want to start with 3, but let's see here, if I go 3, 4 or 3, 3, 3, 3 would be the smallest. And then from there, kind of follow the order. 4, 3, 4. So this would be a 3, 3, 4, 3, 4 semiregular tessellation. And here's some more. You can name them yourself if you want. But these are also semiregular tessellations. And the idea is that take any vertex and go around it. And figure out the number of sides for each of those shapes that you go around and try to write them in the smallest possible order. The following tessellation made up of hexagons and triangles. However, this is not an official semi-regular tessellation. So how is this tiling how this tile breaks up the vertex rule? Well, if I take the one in the far middle, and go around it, that would be 3, 3, 3, 3, 3, 3. So if I just base it on that one in the middle, it would look like 3, 3, 3, 3, 3, 3 semi-regular tessellation. However, if I take one, let's pick this vertex here. There's the 3 and 3, and a couple more 3s, and then a hexagon 6. So this one would suggest 3, 3, 3, 3, 6. So we're getting different names depending on which vertex you choose. And that kind of breaks the rules because the vertices should all be the same. But you can see that we have two different here. So this is not an official semi-regular tessellation. It is a tessellation, but not a semi-regular one. And what about this one? From all the ones that we see, like this one right here, again, let's try this for color. This one right here, that would look like a 3, 3, 4, 3, 4. This one right here looks like a 3, 3, 3, 4, 3, 4. That one also, this one also. So the ones we know are, but the problem is with the gaps. I mean, kind of oops. The problem is, what about the gaps like right here? Or over here? Or over here? Yeah. Can those be filled out from the shapes that we see? Well, if you try putting a triangle and a triangle, you see now we have 3 triangles. And in this case, this vertex right here would have 3, 3, 3 triangles in a row for this to work. And that's going to be a problem. So if we go back, again, for this vertex right here to work, we need 2 more triangles. So that's why I put those 2 there. For this vertex to work with the 3, 3, 4, 3, 4, I would need another triangle. So I added that. But doing so, that gives a problem with this vertex right here. Because now we have 3 triangles in a row. So no, this is not a semi-regular tessellation. And I'll leave this for you, but describe the shape that tessellates the brick wall. You might notice that our shape were basically rectangles. There are a few other ways the shape can be arranged to form tessellations. In terms of why this arrangement is generally used for a brick wall, and that's basically just for support.